In this case study, we have the topology as shown, with the symptom that router 3 cannot ping to router 6 or anything beyond router 6. As shown in the topology, NAT is running on router 4, where Ethernet 0 is defined as the inside portion of the network, and Ethernet 1 is defined as the outside portion of the network. Since we know that router 4 is running NAT, let's take a look at the relevant configuration for router 4. Here we see that NAT is enabled on the Ethernet 0 and Ethernet 1 interfaces. This is where we define which part of the network is considered the inside and which part is considered the outside. NAT is configured to dynamically translate packets based on whether or not they are permitted by access list 7. More specifically, the configuration command itnat inside source list 7 pool let me out indicates that if this router, in this case router 4, receives a packet on its inside interface and the packet is permitted by access list 7, then the source address of the packet will be translated to one of the addresses in the pool labeled let me out. Access list 7 is permitting any packets sourced from network 10.10.3.0 with subnet mask 255.255.255.0, and the NAT pool called let me out contains addresses 200.200.200.1 through 200.200.200.4. Based on the configuration we just saw, what do you think NAT should logically be doing? Here we'll describe what should be happening when router 3 sends a ping packet to the far Ethernet interface of router 6. First, router 3 will send an ICMP packet with a source address of 10.10.3.3, otherwise known as the inside local address, and a destination address of 172.16.6.6, otherwise known as the outside local address. This packet will enter router 4's Ethernet 0 interface, which is defined as an inside NAT interface. Remember, this packet must be permitted by the access list used by the dynamic NAT configuration. In this case, it is access list 7. In this case, we will assume the packet is permitted by the access list and is therefore eligible for NAT translation. Since the packet is to be translated, we expect router 4 to translate the source address of the packet from 10.10.3.3 to the first available address in the NAT pool, which is 200.200.200.1, and then forward the packet to router 6. The packet forwarded to router 6 would now have a source address of 200.200.200.1, otherwise known as the inside global address, and a destination address of 172.16.6.6, now known as the outside global address. The NAT translation table would now have an entry for the translation of inside local address 10.10.3.3 being translated to inside global address 200.200.200.1. The next thing that would happen is that router 6 would respond to the packet it received from router 3. The packet sent from router 6 and received on router 4's outside interface will have a source address of 172.16.6.6, which is the outside global address for router 6, and a destination address of 200.200.200.1, which is the inside global address for router 3. When router 4 receives the packet from router 6, it will check the translation table and find a valid translation for the inside global address of 200.200.200.1. Router 4 will translate the inside global address to the inside local address and forward the resulting packet. The resulting packet will have a source address of 172.16.6.6, the outside local address of router 6, and a destination address of 10.10.3.3, which is the inside local address for router 3. Now that we have an understanding of what should be happening in this case, let's run some debugging on router 4 to see what really is happening and why router 3 cannot ping router 6 or anything beyond. Also, we will limit the output of the debug to only ICMP packets, since these are the types of packets which we know fail. This is the purpose of access list 177 shown above. When the access list is applied to the debug, only only packets that are permitted by the access list will be monitored by the debug. In addition to IP packet debugging, we would like to monitor NAT, so we will enable NAT debugging with the command debug IPNAT. Using an access list as we are doing is extremely important. Otherwise, the debug could quickly use up router resources and cause the router to become inoperable. With both of these debugs enabled, we will be looking for packets that should be exchanged between router 3 and router 6. With IP packet and NAT debugging enabled on router 4 as shown previously, we see the packets as follows. Router 4 first receives a packet from router 3 and translates its source address of 10.10.3.3 to 200.200.200.1. The resulting packet gets forwarded out router 4's Ethernet 1 interface. So far so good. We are seeing what we expect. The next thing we expect is to see a reply packet from router 6. However, we don't see a reply packet from router 6. Instead, we see another packet from router 3 as we saw before. Again, NAT takes place and the resulting packet gets forwarded. And again, another packet arrives from router 3. So, for some reason, we're not seeing any packets from router 6. It could be that our access list, used in the debug, is not permitting packets from router 6, although this is unlikely since we permitted any ICMP packets. Another reason could be that router 6 is not sending packets. If we suspect that router 6 is not sending packets, we should go to router 6 and see if we can find any reason why this might be the case. We could first look for obvious things, such as packet filters that might be denying packets from router 3. For this example, we will assume there aren't any packet filters. Next, we should see if router 6 has a route to the source of the packets it is receiving from router 3. Remember, the packet that router 6 receives from router 3 will have a source address of 200.200.200.1 because of NAT. Here we see that router 6 does have a valid route for network 200.200.200.0. The route is a static route directly connected to the Ethernet 1 interface. The fact that the route is directly connected here is significant. Anytime a device tries to send packets to an address which is on a directly connected network, the device will send an ARP request out in order to get the MAC address for the address. Now that we know this, we can include yet another debug to see if the appropriate ARP packets are being sent. We will enable ARP debugging on router 4 with the command debug ARP. Now router 4 has debug NAT, debug IP packet 177 detail, and debug ARP enabled. The first packet we see from router 3 is the same as before. Router 4 performs NAT and forwards the resulting packet out the Ethernet 1 interface. Now, since router 6 thinks that 200.200.200.1 is on a directly connected network, we see, as expected, that router 6 sends an ARP request for address 200.200.200.1. At this point, we should expect to see an ARP response to the router 6's ARP request. But we don't see an ARP response. Instead, we see another packet from router 3, followed by another ARP request from router 6. This pattern will continue with router 6 never getting an ARP response. So why isn't router 4 responding to the ARP request? The ARP request is for address 200.200.200.1, which router 4 does not own. Therefore, it doesn't respond. We now know the cause of the problem. Router 6 is ARPing for the inside global address of 200.200.200.1, and router 4 is not responding because it doesn't own this address. How can we fix this problem? There are a few ways, two of which are presented. One, we can change the static route that router 6 has for network 200.200.200.0 to have a next hop address of 172.16.4.4, which is router 4's Ethernet 1 interface address. This would cause router 6 to forward packets destined for 200.200.200.1 to router 4 without the need for sending an ARP for address 200.200.200.1. A second solution would be to add a static route for network 200.200.200.0 in router 4, as shown in the example above. With a route in router 4's routing table, if router 6 were to send an ARP request for address 200.200.200.1, router 4 would now respond with its own MAC address because of proxy ARP.